Hello, my dear students. Welcome you all to Sri Jayendra Rank Zone classes. I am your mentor and your friend for the subject chemistry, and I will be taking the organic chemistry. My dear students, as we have started general organic chemistry, today we are going to start with the relative basic strength of amines. Although we have discussed some of the points, how to calibrate, how to evaluate the basic strength of amines. So relative strength of different amines, when we talk about that basicity of amines, of aliphatic amines, is directly proportional to plus I power, that is positive inductive effect. That is electron donating groups or electron releasing groups. More the number of electron releasing groups attached to the aliphatic chain, more will be the basicity of aliphatic chain. Aliphatic chains, especially the aliphatic amines, for example, when we discussed ammonia. So in case of ammonia, nitrogen being more electronegative is having one of the lone pair is attached to three hydrogen atoms. There is no electron releasing group in case of ammonia. But when we compare ammonia with primary amines like RNH2, so here we can see that nitrogen is having more electron density comparatively in ammonia because R is showing its plus I effect. So the R means the alkyl group will increase the electron density cloud over nitrogen atom. Alkyl group will increase the electron density on nitrogen atom, thereby making it more susceptible for the attack of proton. Okay, so this nitrogen is more susceptible for H plus attack, and gaining of H plus increases the basic character. So this nitrogen, which is having more electron density, it is more susceptible for H plus attack, and that is why it is more basic. Okay. So when we compare ammonia, primary amines, secondary amines, and tertiary amine, the plus I effect is more in tertiary amine, increasing order of basic character, increasing order of electron releasing effect. Okay, understood? The basic character of ammonia of amines and substituted amines in gaseous phase is tertiary amine is most basic, then secondary amine, then primary amine, and then ammonia. And the last is, Is it clear? Okay, this is the gas phase basicity. Okay, the order of basicity in aqueous solution is not same as of gaseous solution. Basicity of amines in aqueous solution, like for example, if we are comparing ammonia with methylamines, okay, so if we are taking the R, that is alkyl group, as methyl, okay, so the order will be, I'm taking R as methyl group, okay, so order of basicity of substituted methylamines will be R3N. R3N is tertiary amine. R3N is tertiary amine. Ammonia is less basic than tertiary amine. Then primary amine RNH2, primary amine, tertiary amine, this is ammonia, and then comes the secondary. Why this type of order came, or why this type of order appear in case of basicity? As in case of gaseous phase, we came to know that the basicity is totally dependent upon inductive effect. But the fact is, when the compound is in, it is with some solvent, then there are some more factors which are to be looked upon. Okay, which are to be considered. Understood? So here the order is ammonia, then tertiary amine, then 1 degree amine, then secondary amine. If we take R as ethyl group, then the order will be ammonia, then comes primary amine, then comes tertiary amine, then comes secondary amine. Okay, the order will be ammonia, then the primary amine, then the tertiary amine, and then the secondary amine. The reason is because basicity of amines in aqueous solution does not solely depend upon inductive effect. Okay, the basicity of amines in aqueous solution is not only depending upon inductive effect, it is depending upon the combined effect, but on the combined effect. So it is not solely depending upon the inductive effect, but on the combined effect. The combined effect of inductive, steric, and solvic or solvent effect. So it is dependent upon inductive effect, steric effect, and solvent effect. Understood? So this is the relative order of basicity of amines, which is dependent upon inductive effect, steric effect, and solvation effect. That is why the order comes different from the order of basicity in case of gaseous phase. Okay. Now we are going to discuss about some problems based on these effects. Okay. For example, if you want to find out value of Kb, Kb is dissociation constant. If Kb is high, more will be the basic character. Kb is inversely proportional to pKb. That is, if pKb is high, then weaker will be the base. So if the question Neet 2016, most stable carb anion you have to find out, minus you have to find out the most stable carb anion. First option is this. This is acetylide ion, then C6H5 minus, then so which carb anion is most with stable here in this question? Which carb anion is most stable? Understood? So you can see among all these carb anions, okay, more the number of electron releasing groups, that these it is containing 3 electron releasing group, it is containing 2 electron releasing groups. So these electron releasing groups, they are basically decreasing the stability of carbon ions. Okay, so option number 3 and option number 4 they are not going to be the correct option in this question because they are most destabilized. Third is most stabilized, and fourth is comparatively less destabilized. Now, when we compare the phenyl carbonate C6H5 minus, okay, so C6H5 minus is basically telling us what? That the hydrogen is released in the form of H plus, and the carbon is having a negative charge. So this negatively charged carbon, well, this negatively charged, carbon or carb anion, I should say, okay, it will increase the electron density over this ring. And because of increasing the electron density over this ring, it will decrease the stability of, or it will decrease the resonating stability of this compound. Okay, resonance I am going to come, for the in the next video. Okay, or in the later part of this video only. So the most stable is this compound. Now there is another option. There is another explanation as well. This is sp hybridized carbon, and this is sp2 hybridized carbon. The sp hybridized carbon is more electronegative, so it can precipitate more amount of electron density. It can absorb more amount of electron density. The sp2 hybridized carbon is having less electronegativity. That is why to absorb or to gain electrons is, or it will disturb the stability of the compound. That is why this is more stable and this is less stable. Okay. Now you have to find out which of the, this is again combined pre-medical examination 2008. The same question was the part of All India Engineering Entrance Examination AIEEE 2003. The question was, which of the following compounds is most acidic? CH3COH, CH3CH2OH, CH2ClCOOH, and CCl3COH. Now, as we have discussed, that the acidic character, it depends upon the electron withdrawing groups. Mean more number of the electron withdrawing groups, more will be the acidic character. Understood? So it can be easily seen. See, ethanol, we can easily rule out. Ethanol, they are weaker acids, mean their acidic character is weak than water as well. Okay, so they cannot be the part of this family. We all are having acids. Now the resonating structures of C double bond OH, okay, can be easily settled. It can be easily, enhanced. Okay, or it is more, favorably done by the electron withdrawing groups. So more number of the electron withdrawing groups, more will be the acidic character. Okay. So here there are three Cl attached to the carbon, which is C double bond OH, and that is why it is most acidic in character. So option D will be the correct answer. Okay. Now if you want to compare the basic character of, compare the basic nature of H3O plus hydronium ion, H2O, and OH minus are in the order. Which order they are going to follow? H3O plus is basically protonated water, right? H2O is neutral, it is amphoteric, and OH minus is the conjugate base. Now, basic nature depends upon the stability of anion, stability of conjugate base. So, when water will self-ionize itself, so it will form H3O plus and OH minus. Now, as I have to find out the basic character So this is the conjugate base OH minus. So when water will release H plus to form OH minus, more stable conjugate base. So OH minus will be most basic, then comes water, and then comes H3O plus. Because water was neutral, it was amphoteric, it gains H plus. So when H2O neutral molecule will gain H plus to form H3O plus, it means the electron density on oxygen atom, it is attracting H plus ions to form H3O plus. That is why water is considered to be more basic than H3O plus. Okay. If you want to find out the stability of carb which is most stable carbocation, CH3 CH2 plus, CH3 plus, CH3 CH plus CH3, and CH3 CH2 CH2 plus. This is 1 degree, this is 2 degree, this is 0 degree, this is again 1 degree, and 2 degree is most stable. Now among this and among this carpetine is having a ethyl group, a long carbon chain. And as it is having a long carbon chain which is attached, okay, so the most stable will be this. And among this one and this one, the stability of this compound will be more than this compound. Okay, so these are some possible questions. Now we are going to talk about resonance today. That's a very important topic. Okay, now what is resonance basically? Consider structures of benzene, different structures of benzene. Okay, this is ipso position, this is ortho, meta, and in regarding in comparison to ipso, it is para. Okay, so according to the given structure, the bond length of C1 C2 bond, mean ipso and ortho, okay, should be smaller because it is having a partial double bond. Then C2 C3, okay, because C2 C3 is not having any double bond. C1 C2 is having a double bond, and the double bond, the bond length will be lesser than the single bond. Okay, but on different studies done like X-ray diffraction, spectroscopy, we came to know that bond length are equal. Okay, but the bond length of C1 C2 and C2 C3 are equal. Okay, their bond length comes in between single bond and double bond. So this average bond length concept, when we came to know during X-ray diffraction studies, that okay, it is not a single bond, it is not a double bond. The we can say the average of the single bond and the double bond, or we can say more near to the double bond and less or more far to the single bond. So these X-ray diffraction studies help us to reveal out that bond length. X-ray diffraction studies, spectroscopy, they help us to find out bond lengths are equal. It means the electrons are basically moving, the double bond is moving from one position to the other position. That is why there is a need to draw different structures of benzene. Okay, like for example, this is the first structure. This C1C2 bond is having a double bond. This is the second structure in which C2C3 bond is having a double bond. Understood? One, two, three. One, two, three. So first and second are the resonating structures. Are resonating structures. Understood? So when a molecule or an ion, because of any reason, stability reasons, cannot be represented by a single Lewis dot structure, when any molecule or ion cannot be represented by a single Lewis dot structure, and more than one structure are needed to represent all properties of the molecule. These structures are known as resonating structure. These structures are known as resonating structures. Okay. This phenomena of showing or exhibiting resonating structures is known as what? Resonance. Can be defined as a partial delocalization of electrons or electron density or charge. Okay. Resonating structure have the same arrangement of atomic nuclei, have the same arrangement of atomic nuclei, but differ in distribution of electrons. But they differ in distribution of electrons. Only pi electrons are delocalized. Okay? Understood? The concept of resonance is totally hypothetical. Are hypothetical. An actual structure is a resonance hybrid. Resonance is basically involved when there is conjugation, generally, when there is conjugation of pi bonds that is alternate, double, single, and after double there is a single bond. Then we have the double bond, as in case of benzene, bond arrangement. The conjugation, it doesn't really mean that conjugation always takes place between a pi bond or a a sigma bond. It can be between a pi bond or a charge, okay, pi bond and an electron or whatever it is. Okay, now we are going to talk about the conditions of resonance. Conditions for resonance. Okay, the first condition is planarity, mean sp2 hybridized carbon. The carbon should be sp2 hybridized or sp hybridized. Okay, but it should not sp3 hybridized. The concept of planarity says that either the carbon in the atoms considered in that molecule showing exhibiting resonance, it can be sp2 hybridized or sp, but it cannot be sp3 hybridized. Secondly, existence of conjugation. Conjugation is a system in which p orbitals are arranged parallel and continues to each other and continues to each other is considered as a conjugated system. Okay, The conjugation can involve negative charge electron alternate to pi electron, alternate to pi electron, conjugation, lone pair electron alternate to pi electron, pi electron alternate to pi electron conjugation, pi electron alternate to a vacant p orbital, positive charge, a vacant orbital having a positive charge. Okay, pi electron alternate to odd electron, that is free radical, conjugation, then lone pair electron alternate to vacant orbital having positive charge. So these are the primary requisites, okay, for making of a conjugated system. It can be a negative charge, alternate to pi electron. It can be lone pair, alternate to pi electron. It can be pi electron, alternate to pi electron. It can be pi electron, alternate to a vacant orbital having a positive charge. It can be pi electron, alternate to odd electron molecule that is free radical. And it can be lone pair, alternate to the vacant orbital having a positive charge. Now, the conjugate positions of the molecule, they are the alternate positions like 1 comma 3 comma 5. Okay, like for example CH2 double bond CH, single bond CH, double bond CH, single bond CH, single bond CH. Suppose this is the molecule, so you can see the double bond, then you can see the single bond, then you can see the double bond. Okay, and then you can see a positive charge. These all are conjugate positions like 1, 2, 3, 4, 5, 6. So 1 comma 3 comma 5 are conjugate positions. Understood? A compound having at least two conjugate positions is known as a conjugate compound. At least two conjugate positions. Now, types of conjugations. I will give you one example of each category. First is negative charge alternate to double bond to pi electron. This is a carbonyl, and this carbonyl is alternate when it is located alternate to the carbon which is in a double bond, right? So this is a conjugation. Understood? Here also it is a conjugation. Here also this is a conjugation. This and this is a conjugation. This and this is a conjugation. This and this double bond is in a conjugation. So these are the examples. Okay. Secondly, lone pair electron alternate to pi electron. Examples are lone pair is alternate to double bond. Example. Okay. There is also example. These are the examples of lone pair or alternate to pi electron. Then comes pi electron alternate to pi electron. Okay. Like dienes. Okay. Benzene is also example of this category. 135. Naphthalene, anthracene, they all are examples of this category. Okay. Now next is pi electron alternate to vacant orbital. Having positive charge. Like for example, this one. It is a positive charge pi conjugation. Okay. Conjugation. Okay. Conjugation. All these are conjugations. So these molecules, this molecule and this molecule is having pi bond alternate to pi bond. One of the conjugation, pi bond alternate to positive charge. Okay. Then pi electron alternate to free radical. It is a pi electron alternate to free radical. It is also a pi electron alternate to free radical and pi electron alternate to pi bond. Okay. So all these are different categories of conjugations. Now rules to draw valid resonating structures. The first rule is the flow of electron from high electron density to low electron density should be unidirectional from high to low electron density. Negative charge to lone pair electrons to pi bond electron to partial positive charge and then to positive charge, because partial positive charge is weaker in intensity than positive charge. This should be the movement from negative charge to lone pair, from lone pair to pi bond to partial weak positive, and then to positive. The second point is position of atom cannot change. Cannot be changed. Only the pi electrons are delocalized. The negative charge alternate to pi bond. Only the pi electrons are delocalized. The position of the atom remains same. Okay. This is the resonating form. Now this example is tautomerism. This is a tautomer. This B is a tautomer of A, but it is not a resonating form because the position of atoms have changed. Okay. That is why it is not a resonating form. Third point, second period elements should not violate the octet rule while drawing resonating structures. Okay. For example, this is the second resonating structure. Now you can see the nitrogen is violating the octet rule. Okay. It is not a resonating structure because nitrogen belongs to the second period and is showing 10 valence electrons, which is not possible. This violates the octet rule. Then each resonating structure must have same number of unpaired and paired electrons. Number of paired and unpaired electrons in each resonating structure remains same. Number of unpaired and paired electrons in each resonating structure remains same. For example, this is the second resonating structure, this is the first resonating structure. Here both are resonating structure. Okay, because the number of unpaired electrons remain same. Number of unpaired or paired electrons. Then fifth point, net charge should be conserved in all resonating structures. Net charge should be conserved in all resonating structures. Okay, for example, net charge is 0. This is positive charge. This is negative charge. Here also the net charge is 0. So even after the distribution of polarities, even after the distribution of the charges, separation of the charges, the net charges should be 0. Okay. Now, these are the rules for writing, for drawing a resonating structure. Then how come you will get to know that which structure is more stable? So the rules for stability of resonating structures. What are the rules which will mark for the stability of resonating structures? First rule is, among all the resonating structures, non-polar resonating structures are more stable. Are more stable than polar resonating structures. Okay. As it is considered that more number of covalent bonds is considered to be more contributing than others. This is plus, this is minus. Okay. Here you can see the conjugation is there. Here also the conjugation is there. But the conjugation is not involving the pi bond. Basically, they have released the charges. Okay, they have released the sorry. Yeah. They have released the charges when they have convert the pi electrons into the respective charges. Okay, so this molecule is polar, this molecule is a non-polar, having more number of pi bonds or more number of covalent bonds. That is why it is more considerable, more stable. Second point is, if two resonance structures have same number of bonds, then the structure in which octet of every atom is complete is more contributing. If two structures, resonating structures, have same number of bonds, then the one in which octet of each atom is complete is considered to be more contributing. Is considered to be more contributing. Okay. For example, these are two resonating structures. In this resonating structure, nitrogen is making three covalent bonds. Okay, having its own lone pair. Okay, in this structure, nitrogen is making one, two, three, four covalent bonds with positive charge. Being electronegative, nitrogen cannot accumulate positive charge. And that is why the second resonating structure is less stable in comparison to the first. Okay. The carbon here is making three covalent bonds when it is dividing or it is divided of its octet. Here, the carbon its octet is completed 1, 2, 3, 4. Nitrogen also its octet is completed. So, on the basis of octet, if the number of bonds are same, number of electron pairs are same, okay, on the basis of octet, if we look, then second is more contributing. Second is more contributing than first. Okay. Then the third is if the resonating structures have same number of bonds. If resonating structures have same number of bonds, then the neutral structure is more stable. Then the neutral structure is more stable than charged structure. If both are charged, then the one which is having less charge is more contributed, more stable. Okay. Then next point. In case of charge resonating structures, the most stable one is that in which the positive and negative charge reside on the most electropositive most electropositive and most electronegative atoms. Of the structure respectively. Like for example, oxygen being more electronegative if it is carrying the negative charge, it means B is more stable than A. Okay. Next point, resonating structures in which unlike charges are there. In which unlike charges are closer to each other, mean less amount of charge separation. Will contribute more. Okay, will contribute more. And the next is resonating structures in which like charges are far away. are more contributing as compared to the structure in which like charges are closer. Are more contributing. Understood? So this is all about the resonance. In the next term, we will discuss about the resonance energy and different problems based on the resonance. Okay? And then we will discuss the mesomeric effect. Till then, bye bye. Take care. Stay safe. Stay healthy.